So this is the last chapter in Tom Stoker's book on Introduction to Climate Modeling. I think I will add a few podcasts from David Nealon's book, which is much more focused on modeling climate change. And this last part is also about climate change, but more focused on multiple equilibria in the climate system. And Tom has worked a lot on this problem from simple models, especially this bipolar seesaw and multiple equilibria in the climate system. Obviously, the multiple equilibria directly relates to the Lorenz model, the Lorenz-Salzman model that we looked at, where the system without any external forcing, just due to internal dynamics, can jump from one state to another rapidly and then jump back. So the idea is always to see what the past data say about such possibilities in the climate system and then try to build models to try to understand the processes that could have created these abrupt changes. Okay, so abrupt climate change is recorded in polar ice cores, and some of the most exciting work has come from the data that's derived from these ice cores and ocean sediments. Ocean sediments tend to be not as highly resolved, but nonetheless, here is a good example of the Vostok ice core that has 800,000 years a record in it. So looking at deuterium, O18, dust, methane, and CO2, and benthic delta O18 as well. So these are basically, without going into details, give you temperatures, CO2, methane, and we have talked about the relations between them. And on these millennial timescale, 100,000 year timescale ice ages we have in these time series, we have talked about the abrupt end of the glaciation and the slow build-up, abrupt and slow build-up, and this sawtooth structure in it, and the relation phase lag between temperature, which is driven by orbital change as a start, and then CO2 and methane follow, and vice versa. And we talked about how ice albedo feedback drives a rapid change in the warming phase, where the orbital change triggers a retreat of the glacier, albedo decreases, more energy is trapped, and then there is a rapid retreat of a glacier, whereas the buildup takes longer because as the system begins to cool, initiated by the orbital forcing, the global temperatures begin to get colder and colder. The ability of the atmosphere to hold moisture gets reduced continuously, which means the snowfall rates over the glaciers begin to reduce, so the growth of the glacier begins to go slower and slower. So there are other relations. Dust corresponds to global precipitation changes and how that's recorded in the ice cores and so on. But what is fascinating is that in these dominant 100,000 year cycle that happened in this period, there was another time scale if you go beyond that, but let's not go there. There are shorter time scales which also show abrupt changes, so it's easier to go and look at them. So from the same place, if you zoom in to kilo years, this is also years in kilo years, but here we are zooming in so that you can see much more of these abrupt changes. So if you look at the GRIP, which is from Greenland, and look at the delta O18 and methane, you can see relatively rapid changes of decades. Okay, so this is 200 years here, so that's 50, 100, 150 and 200. So this is happening very rapidly, and this is the West Antarctic ice sheet data, which also shows a correspondence between them. So there is not only changes happening in the Southern Ocean, but also corresponding signatures in the Northern Hemisphere, especially Greenland. You expect that Atlantic meridional overturning circulation and thermohaline circulations changes in the north can induce changes in the south. Changes in the southern hemisphere can translate to changes in the north. But the question is, how fast do these things happen? So can data be used to build a model to capture the time scales and the relation between the changes in the north and the south. So several attempts have been made. We will look at one from Tom Stoker and other authors explaining the time scale of the bipolar seesaw and the relation between the northern hemisphere changes and the southern ocean changes recorded in these ice cores. So this is the climate history of the last 90,000 years recorded in ice cores from Greenland and Antarctica. Oxygen isotope ratio delta O18 in per mil deviation from a predefined standard in the GRIP ice core in Greenland. Delta O18 from bird core from Antarctica, methane concentrations, and so on and so forth. So the main point again is that if you look at Greenland and Antarctica, there are times where there are correspondences between them. So the same in methane, of course, not as clearly. So that the integration time scale of various quantities can be different as you go to smaller and shorter time scales. So if methane is being altered by changes in precipitation, wetlands, permafrost, glacial cover, and so on, that doesn't necessarily have to correspond one-to-one with changes in temperature, for example. Okay, so let's just focus on the northern hemisphere and southern hemisphere temperatures at these millennial timescale oscillations in them. They're called Dansgaard-Oeschger oscillations or events because they are honoring scientists Dansgaard and Oeschger, who did a lot of the work on this. And there is lots of other following work on the timescales. There are lots of data that show millennial timescale variability in the data record, but it should be made clear that we don't have a very solid theory for it because these timescales don't directly correspond to the forcing in orbital timescales, which are much easier at longer timescales. So ellipticity timescale, obliquity, precession, and so on can be used to explain the longer timescale changes, but these shorter ones are not necessarily directly explained by orbital forcing, which is consistent with the Lorentz Saltzman model, that the abrupt changes and jumps from one regime to another happen purely from internal dynamics and feedback. So that's not so inconsistent with the theory of chaos and nonlinear dynamics. The other example that's used a lot for abrupt climate change, which is more specifically relevant for the global warming and the loss of glaciers over Greenland and Antarctica and the acceleration of the glacier melt and so on. So we came out of the last glacial maximum around 21,000 years ago, and the warming triggered by the orbital forcing, even though there are other theories, show Heinrich event 1 here, and the Bowling-Allarod, which is another millennial timescale event, Younger Dryas, which shows an abrupt. So there was a warming that started in Greenland, and then something happened, and there was a cooling, and again, there was a warming and an abrupt cooling before we came out of the ice age to the current state approximately, and what we call the Holocene, with little blips within the Holocene as well, the so-called 8.2 year cold event. And there are lots of papers discussing what drove these, and they do correspond to changes in the Atlantic meridional overturning circulation. So if you zoom into this, you can see that these changes happen on extremely short time scales, which is very critical, because with global warming, if there are such abrupt changes possible at a time scale of a decade, then obviously we are pushing poking the climate dragon, as Wally Broker would say, with a stick, and a sudden collapse of West Antarctic ice sheet or some big part of Greenland can do lots of damage in terms of sea level rise and so on, combined with the global warming. Okay, so this is looking at air temperatures and accumulation in meters per year. So basically showing that abrupt climate changes are recorded in ice cores. So we will come back and look at the theories behind them and the modeling. So the main thing to remember is that data give us some information on the timescales that are seen in these records, and then the idea is to build models, simple models to explain them, and then hopefully look for them in fully coupled models. And we will see that there are differences in the timescales produced by the simple models versus ocean models in terms of the time scale of these some of these oscillations at millennial timescales. Okay.